So this video looks at how to conduct sunlight on amenity analysis, which is particularly relevant in the UK context. And what you will need is Rhino, Grasshopper, and Ladybug installed on your computer. So I have kept the length of the script as short as possible and without using complex referencing methods or creating interactive UI elements. The idea is that any user with basic Grasshopper and Ladybug knowledge should be able to reproduce the script by following this video. And now I'm going to show you how the analysis can be conducted according to BRE guidelines. First, you have to let Ladybug fly in your Grasshopper script by simply typing ladybug ladybug. And then we can add in other inputs such as the weather file as well as the geometries that are already prepared in Rhino. When it comes to weather file, you can go to this website provided by Ladybug to download the weather file that is closest to your project location. In this case, I'm going to download the London Gatwick weather file, and I can just copy the location of the IWEC weather file to be pasted in Grasshopper and later read by Ladybug. And in terms of Rhino geometries, I would just simply reference them in manually. But of course, if you have other methods to reference your geometries according to layer, for example, you can, of course, you can do so. After referencing all the geometries, including the context mesh, building footprint, and the analysis surface, we can then use Ladybug download weather file to read the URL link that we pasted in Grasshopper previously. So the output we are looking at is the EPW file, which we will then use Ladybug import location to extract the location as an input for Ladybug SunPath. And what I normally do now is to assign the center of the analysis surface as the center point of the SunPath. And now you can see the SunPath is nicely located around the analysis surface. We can also merge the context mesh and the building mesh to be used later. Another important input that we need to assign to Ladybug SunPath is the HOIS, which stands for Hour of the Year. And we can use the Ladybug analysis period component to extract the hours for the analysis. And according to BRE guidelines, it is recommended to use the sun hours of 21st of March for the purpose of this analysis. So we can go ahead and put 3 for both start month and end month, and 21 for both start day and end day. And taking London as an example, and the start hour of the day would be 6 a.m. when the sun rises, whereas for the sunset it would be around 6:15. So we can put 7 for the end hour so that the last few minutes after 6 will still be covered. And for the time step, we will put 60, which means for each hour we will be calculating minute by minute. And now we can plug in the HOIS of 21st of March to the HOIS that the SunPath component has asked for. And here I'm just gonna do some tidying up, straightening the wires, etc. So I'll just fast forward a little bit. So the SunPath has been constructed around our site, and some of the outputs from the SunPath component will be used later for analysis. And normally at this point, I would plug in mediating component to store the data from the outputs to be used later. Because this way I found that it's much cleaner, and when the script gets very complex, you can always trace the data back to its source. And I'm gonna change the view to perspective so we can see everything more clearly. One of the outputs that will be used but needs filtering is the altitude, because according to BRE guidelines, sunlight at an altitude of 10 degrees or less does not count. In other words, we'll have to filter out the altitudes that are less than 10 degrees or larger than 170 degrees. In order to do that, we can write an expression in Grasshopper by typing in expression and then simply double click the component to edit the expression. So it would be basically an if statement to check if A, in this case altitude, is larger than X, at the same time smaller than Y. And if A meets both criteria, the statement would be true. Otherwise, it would be false. And if we zoom into this component, we can add an input, which would be A, and then we can connect the altitude to A, and the X in our case, it would be 10, and the Y, 170. We'll now use Ladybug direct sun hours to compute the number of sun hours received by the analysis surface. And the first input this component asks for is vectors. And this is a vector that was previously outputted from the SunPath component. But before we plug in the vectors, we will have to filter them to make sure that all the vectors would have a sun altitude between 10 degrees and 170 degrees. So we can use the pattern from the if statement to filter the vectors. And if you plug in a text panel to the output of the expression, you'll basically see a list of true and false values that answer the if statement. And now we can plug in the filtered vectors to the vectors input. We can skip the second input because previously we already defined the time step in the analysis period component. And the third input geometry would be the analysis surface where direct sun hours would be computed on. So here we can plug a data component after the analysis surface to go into the geometry input. The fourth input, context, would be the combined geometry we previously merged together. So here we can also plug a data component to go into the context input. Now this would be a cosmetic step that I also did previously to the analysis surface. If you right-click on the data component, you can change its name to combined mesh, for example, and then right-click again to change the Y display to hidden. And now we can move it to the right and plug it into the context input. And this way you will be able to know where the data comes from. At the same time, your script would look much neater without too many wires entangling with each other. For the next input, grid size, we'll go back to the BRE guidelines, where it says the space is divided into a grid of points with a recommended spacing of 0.3 meter or less. So we can quite simply double click to type in 0.3 and plug the slider to the grid size input. Please be mindful that I can put in 0.3 directly because my Rhino model unit is in meter, and Grasshopper would basically follow whatever unit that is in Rhino. And this is also relevant for the next input offset distance. So this is a number for the distance to move points from the surface of the input geometry. And the default offset distance is 10 centimeter. That basically means that when the direct sun hours component is running later, each point on the analysis surface would be elevated 10 centimeter upwards. And because the Rhino model unit is in meter, so we will have to put in 0.1 for the offset distance. I'm not gonna customize the next input legend parameter. I will just keep it as default. For the CPU count, you can also keep it default, which basically is one less than the number of CPU currently available on the machine, or one if only one processor is available. I put a boolean toggle. Yeah, I don't know why I did that. Please don't do that. You can simply just leave it out. And the last input would actually be a boolean toggle for run. So if you toggle it to true, then the direct sun hours component will be running the calculation. In this case, the computation takes 2.4 minutes to run, but that's with only one CPU because I use the true value from the boolean toggle as the input for CPU count, which equates to 1. But if you actually use more CPU, the component should take less time. Before we look at the results in more detail, I'm gonna tidy up a little bit, turning off the preview for all the components except the sun pass and direct sun hours. I'm also gonna turn on the layer which contains my context geometries in the Rhino model. And now we'll be looking at some of the outputs from the sun pass and the direct sun hours components. Apart from the vectors that we previously used, sometimes it will be useful to visualize the sun points where those vectors are from. So here we will be using the data component again to store the sun points, and using the pattern that we previously defined to filter through the sun points so that only the sun points that are between 10 degrees and 170 degrees are selected. And here I'm just organizing the components a little bit, grouping the inputs for the direct sun hours component. And because the sun points are actually just points, we can turn them into 3D geometries such as mesh sphere to see them more clearly. So we can plug the filtered sun points to B, which would be the base planes of each mesh sphere. And for radius, maybe we can use 2 meter. And now you can already see a thicker curve in the Rhino space, which consists of all the sun points on 21st of March between 10 degrees and 170 degrees in altitude. I'm gonna turn off the preview of the mesh sphere as well as the sunpass component. I'll use the custom preview component to visualize those sun points. And assign a color to them, something like yellow, for example. So now we are seeing all the sun points of that day at once, but we can use the list item component together with the slider to visualize the sun points one by one. Because there are 597 points in total, so for the slider we'll put in between 0 and 596. And now if we plug the I output from the list item to the B input of mesh sphere, then we'll be only seeing one sum point at a time. As a habit, I'm gonna group these components together and turn the preview of the list item component off. And now if I slide the slider, we will be able to see the sphere in the Rhino space moving. But maybe the radius is a bit small, so I'm gonna change it to 4 meters maybe. Yeah, so now it's a bit clearer. And now if we slide again, that's from sunrise to sunset and sunset back at sunrise. We can also look at analemma, but we will use custom preview line weights component to visualize this output. If we plug the analemma to the G of the preview component, we can already see a series of curves in the Rhino space, which looked a bit like the number 8. And we can also add a color swatch, for example orange, to shade these lines. These curves basically represent all the sun positions seen at a fixed location, in this case the center of the analysis surface, over the course of 1 year. So for example, this is a picture from Wikipedia, and if you are to take a photo of the sun throughout the year from a fixed location and at the same time of a day, you would end up seeing the change in the sun's position. You can also explore some other outputs of the component and try to find out what they mean, and perhaps even visualize them. But for the purpose of this video, I'm going to jump to the outputs of the direct sun hours component and show you how we can tell if the surface we are analyzing satisfy BRE recommendations. We will use the data component to store the information, that is, the analysis surface, which now has been turned into a mesh, and the sun hour results for each point on the grid. However, please be mindful that the results here are the number of minutes instead of hours, because previously we already defined the time step in the sunpass component to generate some points minute by minute. And then we will copy the data component to store the points on the analysis surface. Let's also turn off the preview of these 3 data components. And with the default legend parameter, the direct sun hours component is already visualizing the results as a heat map, which you can see in the Rhino model. However, the points within the building footprint are also included in the calculation, which should actually be excluded. So we'll use the pointing curve component to check whether the points are inside or outside the building footprint curve. And we'll go back to the beginning where we have the input that contains the building footprint curve and copy it over to plug into the C of the pointing curve component. The relationship output would produce a pattern that indicates the points that are outside, coincident, or inside the curve. We can then use this pattern to call the point that we want or we don't. So we can use the call pattern component and plug in the list of points and the pattern. In this case, we get the points within the building footprint curve, which are highlighted in green. So we can invert the pattern in order to select the points outside the curve. At the same time, we will also have to modify the analysis mesh, so we will use the call faces component to filter mesh faces with the same pattern we used for the points. And I will turn off the preview of the call pattern and pointing curve components, as well as the direct sun hours component, and we would be able to see that the heat map of the analysis surface now excludes the building footprint. But how do we actually now check whether the site we are analyzing meets the BRE recommendations or not? So in the guidelines, it says that as a check, it is recommended that at least half of the amenity areas listed above should receive at least 2 hours of sunlight on 21st of March. Now, I'm not going to go into details of what amenity areas are or how you should count them, because I think it is less of a technical issue but more dependent on project specifics. I will focus on showing you how to calculate the percentage of the area that receives at least 2 hours of sunlight. First, we will translate the sun minutes into sun hours by dividing the minutes by 60. And we can plug a text panel to see the results and a data component to store the sun hours. And we need to filter the results only for the points outside the building footprint with the same pattern we previously used. So we can just copy and paste the call pattern component, but replace the list of inputs with the sun hours. And now we will use the larger than component to create another binary pattern, which would filter the sun hours into two groups, larger or equal than 2 hours or less than 2 hours. We will then use the pattern from the equal or larger than output to further call faces of the modified analysis mesh. And I'm going to flatten the pattern and invert it. And now the component should have removed the mesh faces that receive less than 2 hours of sunlight. So if we turn off the preview of the first call faces component, we should be able to see it more clearly. So these are the areas that receive at least 2 hours of sunlight. And if we don't invert the pattern, we would see the areas that receive less than 2 hours of sunlight. To make it easier to visualize later, we can copy the call faces component and invert the pattern so that we have the two areas separated. And instead of the heat map from the direct sun hours component, we can use mesh color to assign single colors to the areas. For example, for the areas that receive less than 2 hours of sunlight, we can use blue. And if we turn off the preview of the two call faces components, we will then see the areas in single color. And we can copy the mesh color component together with the color swatch to visualize the areas that receive at least 2 hours of sunlight, and maybe change the color to something warmer, such as yellow. As a result, we have the surface we are analyzing in two contrasting colors. And the question we have to answer now is whether at least half of the areas receive at least 2 hours of sunlight. We can use the area component to calculate the total area of the analysis mesh without the building component and the area of the mesh that receive at least 2 hours of sunlight. And now we can just use the division component to calculate the percentage of the analysis mesh that receives at least 2 hours of sunlight. We can plug in a panel to see the result. So in this case, only 33.8% of the area receives at least 2 hours of sunlight. So it is not going to satisfy BRE's recommendations.